Hey everyone, it's Mr. Canfield, BC Calculus, Chapter 17, Infinite Series. Okay, so we've looked at sequences, now we look at series. Sequences are where it's a bunch of things listed off. Series is a bunch of things added together. And then we're looking at the word infinite with them. So we're gonna add an infinite number of things together, which, if you've made it this far, you probably realize that even though we're adding an infinite number of things together, they somehow are going to add up to not infinity every time. Because what? Isn't that weird? Isn't that weird? So let's look at our notation. So in general, you're going to see this guy. This is sigma. And a lot of times you'll see I at the bottom. Sometimes you'll see J, I think I've seen J. So you'd be like I equals 1, and this is where it ends. So if you saw like 4 up here, and then you saw an N like this, what this would mean is 1 plus 2 plus 3 plus 4. If you saw I equals 0 and then a 3, and then let's say you saw 2n, then you would have 0 plus 2 plus 4 plus 6. Right, so I plug in 0, I plug in 1, I plug in 2, I plug in 3, and then I stop. So I plugged in 1, plugged in 2, plugged in 3. I mean, 0, 1, 2, 3. So this is what summation notation looks like. It's how it works. And yeah. So you'll notice we have infinite series going from 1 to infinity, and we'll put a like plus plus dot 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 plus rah, 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 you know, all those things. Sometimes we'll see it just as a list like this. You've definitely seen stuff like this before. You know, maybe not realizing that you've been looking at something kind of formal, but there it is. So we've got two versions, or two options for infinite series. Infinite series, either converge or diverge. And that is like, that's gonna be a big focal point for the next few chapters is, does this series converge or does it diverge? When we were looking at sequences in the last chapter, it was as simple as taking a limit and knowing where the terms go. Oh, the terms are going off to 0. Cool, it converges. Oh, the terms are blown up to infinity. Oh, diverges. Series get a lot more complicated. So, in terms of being able to figure out, hey, does this converge or does it diverge? So, these are examples of divergent series. Let's talk about how we know so easily that they diverge. Let's just look at a couple of terms of this. So this is gonna be 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4. So I already know this is gonna be divergent, and the way that I know that is we're gonna be adding a bunch of things together, right? Well, if the stuff that you're adding keeps getting bigger, then as you go off to infinity, like eventually we're adding 2 to the infinity. That is infinitely large on its own. The terms themselves here are getting infinitely large. So this has to diverge. So that was 1. So, and you're gonna be writing converge and diverge so much. I was even using C and D, but you do you. So in our second one here, we are looking at the sum of the square root of n. And you might be like, well, square roots are tiny. Sure. So the square root of 1 plus the square root of 2 plus the square root of 3 plus the square root of 4. Even though these are much smaller than this one, we eventually are going to be adding the square root of infinity, which is infinitely large, even though it's a square root of infinity. Like, it's still infinitely large. So it's going to diverge. And then we'll look at our next example to throw a wrench into the machine. 2 to the 1 plus 2 to the 3 plus 2 to the 4 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 plus 2 to the also, if that idiom doesn't make sense to you, imagine a machine with a bunch of moving gears and stuff like that, and then throwing a metal wrench. Wrenches are typically, not easy to break. So imagine a wrench flying in between two gears that are turning, and then they grind up against that wrench, and the whole machine starts to break down because that wrench is that. Like, that's what this is. That's what this is. Because it's like, oh yeah, so if we're going off to infinity, if the terms are going off to infinity, of course it's divergent. It's not going off to infinity though. This time, if I plug in 0, I get cosine of 0, which is 1. If I plug in 1, I get cosine of pi, which is -1. Then plus 1, -1, plus 1, -1, plus 1. So this is not going off to infinity. Plus 1, -1, plus 1, -1, plus 1, -1. So here's the question. Does this add up to 1? Does this add up to 0? Does this add up to -1? Where does it stop? It's going forever, so it doesn't stop. There is no convergence. This is oscillating. So that's why this is divergent. So divergence happens when when the terms are not approaching a number or when they're approaching infinity. It's guaranteed divergent. Those are the easy cases. Now let's look at less straightforward. So here we go. One way that we determine convergence, and this is one of the most effective ways and also one of the most annoying ways, is to generate partial sums. So what we can do is we can generate S sub 1 just by plugging in 1, right? Well, let's get the terms first. So this is going to be 1 over 2 plus 1 over 2 squared, right, which is 1 over 4, plus 1 over 2 cubed, which is 1/8. And because I spent so much time in pre-calc being bored writing my powers of 2, I've got these way too quickly memorized. Additionally, if you like computer stuff, you probably have the powers of 2 memorized to a degree. You might notice that usually USB drives come in increments of these. So anyway, so if we look at S sub 1, it's just that first term, right? But S sub 2 is not the second term. S sub 2 is the first 2 terms added together. That's a half plus a quarter. Easy way to do this is like the last one's going to be your denominator. So I've got 2 quarters plus 1 quarter. That's 3 quarters. S sub 3, I'm doing that plus that plus that. Well, I know that these two add up to 3 quarters. So then maybe I'll just write that under here to remind myself. If I'm trying to get this to be eighths, then this is 6/8, so this is 7/8. S sub 4. Why am I writing these vertically? I think because Stu kind of had them vertically here. How far does he go? He goes to S sub 4? Okay. By this point, you might already see the pattern, but so this is 7/8 here. If I add on 16ths, this is 14/16, so this is 15/16. So in case you're missing it, maybe writing them, and again, this is a very challenging way to find out if a series converges or not. We're gonna learn shortcuts where we look at that and we know, oh, it converges. We're not generally gonna care what it converges to. This is also, using what we call using partial sums is actually a way to find out exactly what this series is going to converge to. Okay. And this is a strange result. I mean, generally, series are strange results. Okay, so 1/2 plus 3/4, or wait, sorry, these are my, not plus. 1/2, then we're at 3/4, then we're at 7/8, then we're at 15/16. Well, if you notice, this is going up by powers of 2, so like the next one's gonna be 32. What are all these numbers? They're 1 less than the bottom number, so this is gonna be 31. Our next one, 64, it's gonna be 63. So if we think about this in terms of just an n situation, dot, 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 comma, showing space, I know this is gonna be 2 to the n, but what's the top gonna be? It's gonna be 2 to the n minus 1. And this is our nth term. Whatever the nth term is, it's gonna be 2 to the n minus 1 over 2 to the n. And that's 2 to the n, get it, and then subtract 1, not 2 to the n minus 1. All right, so if I'm trying to find the limit as n approaches infinity, what would the limit as n approaches infinity of this term be, of our sum? So like we could say our nth sum is equal to 2 to the n minus 1 over 2 to the n. So as the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n, what is that going to be? You can use L'Hopital's rule if you're not sure. You can use your general understanding of horizontal asymptotes. This approaches 1. If you add these together and you keep going for literally forever, when you reach forever, you hit 1. You never reach forever, you never actually reach 1. But if you were to infinitely add them together, you would get 1. If there's not some level of cognitive dissonance here, there should be. And by cognitive dissonance, cognitive, mental, brain, dissonance, like friction, problems, like ow. There should be some level of like, what? Let that be there. It's okay to have that. You're not going to believe every result that we get in your bones, and it's okay. You'll get there. Like I feel this and believe this now. So let's talk about how we know this to be true. Like this actually is true. Let's maybe think about it. So let's say that this thing right here is 1, right? So if I look at something that's half as tall as it, and then I add something, now a fourth is half of what's left, isn't it? So then if I add this, and I'm just kind of eyeballing it here, but add on half of what's left. And then add on, if that's what's left, so this is like this is where I'm trying to get, right? Add on half of what's left. 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 If you keep on adding on half of what's left, eventually there's going to be very, very, very little left. And if we were to go forever, then there's going to be nothing left. Like that, 2 to the n winds up giving us half of what's left each time in our next term. So yeah, this is a convergent series. This was a lot more work than the previous ones where we couldn't just look at it and know. And in general, what we're going to say is if the term itself, without doing any of this analysis, if this guy goes to 0 on its own as we go out to infinity, we have to do investigation. If this does not go to 0, guaranteed the series diverges. So anytime this goes to 0, we have to do investigation. All right, let's see. Oh, I love this next one. 0.9 plus 0.09 plus 0.009 plus 0.0009. This is, I love this one. It's so fun. It's kind of painful too. So if we look at our partial sums are going to be 0.9, that's going to be S1. S2 is going to be 0.99. S3 is going to be 0.999, then 0.999. So it's a string of 9s. If we were to look at the infinite sum of this, it's 0.9 repeating. What's 0.9 repeating? Do you know? If we do this for literally forever, we get 0.9 repeating. That's 1. So stick around if you want to see a proof of why 0.9 repeating is 1. If you don't want to see a proof of it, then you can stop the video here. In the next video, we're going to move on to the next page and continue on. Okay, so now that they're gone, let's look at this. No, okay. So if we said S is equal to 0.99999, right? Then what's 10S equal to? We'll just multiply this by 10, right? Move the decimal point over 1, 9.99999, right? So what would happen if I take 10S and I subtract S from it? That's the same thing as taking 9.999 and subtracting S from it, right? We're saying S to be like the sum, right? So, okay. Well, let's do some simplification, right? What's 10S minus S? 9S. Okay. And that's equal to 9.999 ... minus S. Wait. But instead of writing S, I could write 0.999, right? So I could say 9S is equal to 9.999 minus 0.999. Wait a minute. 9 point infinite nines minus point infinite nines. That's equal to 9. Divide both sides by 9. You get S is equal to 1. So yeah, 0.9 repeating is the same thing as 1. It's not that it's close enough, it's that it actually is the same thing. These are what we would call two different representations of the same number, the same place on the number line. And don't pretend that this is easy or common sense or duh. It's not. This is a sticky, weird thing. They're the same thing. That's okay. This is definitely something, if you're interested, there's stuff you can study about this. And I would encourage you to feel free to, have problems with this, but it's true. So, yeah, I think while we're here, if that was fun, let's just let's do one more. This is just for fun. So let's say A is equal to B, right? So, well, then that means if I multiply both sides by A, then I could say A squared is equal to AB, right? So, and remember, A is equal to B. So let's add A squared to both sides. And then on this side, I'm going to add an A squared, so A squared, A squared plus AB. Over on the left-hand side, that means that we have 2A squared. On the right-hand side, we have we have 2A squared, and then on this side, we have A squared plus AB. So I can, as long as I do something to both sides, who cares, right? 2A squared, I'm going to subtract 2AB from this side. So I'm going to do the same thing to the other side. 2A squared minus 2AB, and on this side, wait, A squared plus AB minus 2AB, I could rewrite this on this side as A squared minus AB, right? And over here we got 2A squared minus 2AB. So I'll factor a 2 out of this one and get a squared minus ab, and on this one, I'll factor, well, I mean, I guess you could factor a 1 out if you want. And then if I divide both sides by a squared minus ab, divide both sides by a squared minus ab, I get, let's see, cancel, I get 2 is equal to, wait. Shoot, I gotta go. No, just kidding. So I wanted to bring this up because to me this feels very similar to this. There is an algebraic fallacy in this. There's not in this. So even though this deals with these weird numbers, everything here is a valid legal move. There is a singular illegal move that we do here that allows us to say that 2 is equal to 1. 2 is equal to 1 so long as a squared minus ab does not equal 0. If a squared minus ab equals 0, we're dividing both sides by 0, and that's illegal. But ladies and gentlemen, a and b are equal to each other, which means a squared minus ab, I could actually rewrite that as a squared minus a times a, or a squared. That means a squared minus a squared has to not be equal to 0, which means this is impossible. So at this step right here, what we really have is 2 times 0 is equal to 0. And then we divided both sides by 0. This is not part of our course, it's just fun.